Very good morning to one and all. I'm Dr. Abi Meenashy, Senior Resident from the Department of Anesthesiology, and today's class is on physical laws of vaporizers. Why do we need to know about the physics of vaporizers? It's because a vaporizer is an equipment. So, in order to know the working mechanism of any equipment, we need to know the basic physical laws governing the mechanisms. By the end of this class, you guys will be able to understand the various laws in regard to heat, vapor, and its pressure. To apply these laws to understand the design and mechanism of a vaporizer, to understand these laws that govern the administration of inhalational agents. Basically, you need to know the difference between vapor and gas first. As you know, this is actually synonymous, but there is a physical difference between them. Vapor in a gaseous phase of a volatile substance that is normally liquid at room temperature and at atmospheric pressure. Gas is a substance that exists only as a gaseous phase at room temperature and atmospheric pressure. A volatile substance, this can be a liquid at room temperature and atmospheric pressure. When it becomes a gas, it is called a vapor. A gas will only be in gaseous state in room temperature and atmospheric pressure. It doesn't have a liquid state. So there is this temperature called critical temperature, above which the gas will always stay gas and below which the gas can become liquid. So the difference between gas and vapor is gas will always stay in their gaseous state. A vapor, when it goes below the critical temperature, it will become a liquid. Okay, so what is this vaporizer? Vaporizer is a delivery agent for the inhalational agents. So you need to know what inhalation agents are. I'm sure you are aware of isoflurane, sevoflurane, halothane, everything we use in our day-to-day OT basis. Vaporizer is a delivery device that changes a liquid anesthetic agent into its vapor and adds a controlled amount of this vapor to the fresh gas flow into the breathing system. As you know, we set the fresh gas flow that is to be delivered to the patient. What vaporizer does is, vaporizer is an equipment. You fill that equipment with the liquid anesthetic agent that comes in bottles. I'm sure you guys are aware. This vaporizer will turn that liquid into a vapor and add this vapor at a controlled amount as it, whatever the anesthetist sets. And this vapor will be added to the fresh gas flow. Okay. What is vapor pressure? Molecules of this volatile liquid escape into the gaseous form and bombard with the walls of the containing chamber. As you can see here, there are molecules in the down, there are molecules arranged, and above the molecules are escaping from the arrangement and bombarding with each other. We are filling this volatile agent into a vaporizing chamber, that containing chamber. Inside that, these molecules will bombard each other. Pressure exerted by these molecules over the container is called vapor pressure. Vapor pressure tends to differ with each agent. It's not identical for every agent. Substances with high propensity to evaporate generate vapor rapidly. So vapor pressure is dependent on temperature. Higher the temperature, higher will be this bombardment, higher will be the vapor pressure. In temperature, when the temperature is high, you know all the molecules will become loose and hit with each other. So when temperature increases, the bombardment increases, vapor pressure also increases. Directly proportional, it changes along with the temperature. It is unique for each volatile agent. I told you that. Saturated vapor pressure. Saturated vapor pressure is a vapor pressure at a constant temperature where there is equilibrium that is developed between the liquid and vapor phases. There is equal amount of liquid and vapor phases, 50% liquid and 50% vapor. That at that time, whatever pressure that is exerted from that vapor is called saturated vapor pressure. So you need to know saturated vapor pressure is the same like your vapor pressure, but at a constant temperature where there is only 50% of liquid and 50% of vapor. Okay. Saturated vapor pressure is a measure of the volatility of the liquid anesthetic agent. The anesthetic agents, that is your inhalational agents that come with a high SVP, will require smaller proportion of total gas for flowing through the vaporizer to pass through the vaporizing chamber to produce a given concentration. Okay. So higher the SPP, higher will be the volatility. What will happen? Fresh gas flow that whatever we are setting in the flow meter will go inside the vaporizer, will get into contact with your liquid agent, that is your anesthetic agent that you are filling, will get into contact and then it will become a vapor, then it will be delivered to the patient. Anesthetic agent with high SVP required a very little proportion of total gas only to flow because it will get volatile very rapidly. Okay, boiling point, again, boiling point is unique for every inhalational agent. It changes with their volatility also. The temperature at which the saturated vapor pressure becomes equal to the atmospheric pressure. That is called boiling point. At this point, the entire liquid changes into the vapor phase. So, initially we thought saturated vapor pressure is the time there is 50% liquid and 50% vapor. So, a temperature at which the SVP will become equal to the outside atmospheric pressure is where the liquid will become a vapor. In the ambient pressure is decreased. If the ambient pressure is decreased, so is the boiling point. So ambient pressure is your OT temperature. If OT temperature is decreased, the boiling point will also be decreased. We don't want the agent to boil in room temperature because once it starts boiling, all the liquid will be turned into vapor. We don't want that. So here are several inhalation agents and their boiling point and SVP. Okay, here you have ether. Ether, the boiling point is 36.5 degree Celsius. And the SVP at 20 degree is 440 millimeter of mercury. Like, you know, boiling point is measured in degrees of centigrade and SVP in millimeter of mercury. Like that you have for trilene, halothane, enfluorine, isofluorine and desfluorine. You need to remember them. Okay, next entity is latent heat of vaporization. Molecules of the liquid are actually held together by means of cohesion. So energy is consumed during the process of conversion to liquid to vapor phase. Okay, when a state of matter is being changed, some amount of energy is required for this conversion. The number of calories that is required to change 1 gram of liquid into vapor without change in temperature is called latent heat of vaporization. I repeat, the number of calories that is required to change 1 gram of liquid into a vapor without change in any sort of temperature is called latent heat of vaporization. Energy for vaporization comes within the liquid. As energy is consumed, vaporization happens, energy is consumed, there happens a loss of temperature of the liquid. As it continues to happen, the liquid becomes less in temperature. As a result, vapor pressure and subsequent vaporization will also decrease. Like I told you, if temperature increases, vaporization increases. If temperature decreases, vaporization decreases. Okay, so when energy is being consumed, vaporization happens and there is subsequent loss in temperature. We cannot let that go because once it is very low, further vaporization will not happen. So we have to compensate by outside energy source, vaporizer out, or else the vaporizer output will decrease. So you need to know that latent heat of vaporization is the number of calories that is required to change 1 gram of liquid into 1 gram of vapor without changing temperature. As we know, once energy is consumed, the temperature is going to fall. As rapidly it vaporizes, rapidly temperature will also fall. At one point, the temperature will be so low that you have to compensate it with the outside energy source in order to keep the output going on. If at all, it will decrease. Okay, so here is the liquid. Liquid is boiling and turning into gas. Liquid, the molecules of the liquid vibrate with each other and move along with each other by cohesion. And when it's a gas, they move randomly in high speed. Okay, specific heat. The number of calories required to increase the temperature of 1 gram of substance by 1 degree of Celsius is called specific heat. Vital consideration for the design, operation, and construction of a vaporizer. So, you know that each and every inhalational agent has a separate specific heat, has a separate boiling point, has a separate SVP and another density. So all these vaporizers should be tailored for each and every inhalational agent. Since they vary so much in their boiling point and specific heat, we need to design it according to that agent. So every vaporizer is unique to every agent. Thermal conductivity, speed at which the heat flows through the substance to higher thermal conductivity becomes better conductors of heat. Vaporizers are made of material with higher thermal conductivity to maintain a uniform internal temperature during vaporization because we don't want any fall in temperature. As it allows to absorb environmental heat, so there is better thermostabilization. Copper is more thermostable when compared to aluminium. Aluminium is more thermostable when compared to steel, and steel is more thermostable when compared to glass. Okay. Here we have listed various metals and their specific heat and their thermal conductivity. Okay. Basically, how does a vaporizer work? We set the fresh gas flow. We set our nitrous and oxygen. Fresh gas flow enters the vaporizer. Splitting of gas flow occurs. There are two chambers. One is bypass chamber. In the bypass chamber, the fresh gas flow just goes away without getting in contact with your liquid anesthetic agent. Only one part of the fresh gas flow will enter the vaporizing chamber. Inside the vaporizing chamber is your liquid anesthetic agent. So what will happen? Fresh gas flow enters, splits into two halves. That is your vaporizing chamber and your bypass chamber. Majority will go into the bypass chamber only. Only a little fraction will go into the vaporizing chamber. Gas that is going inside the vaporizing chamber will get saturated with the inhalational agent and will exit the chamber and will get mixed with the bypassed gas. Bypassed gas is simply just your fresh gas flow. It doesn't get saturated with any of your vapor, bypasses this and goes inside. Both these gases get mixed. Diluted gas vapor mixture will come out of the outlet and this is being delivered to the patient. That is required for the maintenance of anesthesia. Okay, you can understand this better. Fresh gas flow enters. This violet molecules is your fresh gas flow. This is your splitting valve. That is according to your control dial. If you increase your control dial, lot of gas will go into your vaporizing chambers. If you decrease it, only very less fresh gas flow will go into your vaporizing chamber. Okay. So this is your bypass chamber. It enters like this and goes out like this. No change in their saturation or anything. Here the fresh gas flow comes like this, flows through your either liquid anesthetic agent, gets saturated. These pink molecules are your liquid anesthetic agent, will get saturated. So I'll just give you a scenario. These violet molecules are nitrous and oxygen. Nitrous and oxygen come like this. In the bypass pathway, they just go unchanged. They just go like this. Here is your isoflurane. Just consider this is your isoflurane. Isoflurane, what happens? It comes, your nitrous, your oxygen gets saturated with your isoflurane and comes out like this. So here the gas from the bypass chamber will get mixed with the gas from the vaporizing chamber. You need to know that this is bypass chamber, this is vaporizing chamber containing your liquid anesthetic agent. Okay, how do we express the concentration of these gases? There is this Dalton's law that explains it via partial pressure. Dalton's law states that the total pressure of mixture of gases must be always be equal to the sum of the partial pressure of the total component gases. Okay, consider the component gases as three: oxygen, nitrous, your agent. Total pressure is equal to partial pressure of oxygen plus partial pressure of nitrogen, nitrous oxide, plus partial pressure of your agent. The partial pressure exerted by the vapor of a liquid agent depends only on the temperature of that agent. The highest partial pressure that can be exerted by a gas at a given temperature is called its vapor pressure. We have read about vapor pressure initially. Volumes percent, that's how they express the concentration of the gas. It is the number of units of gas in relationship to a total of 100 units of volume of the total mixture. That's how they express it as volumes percentile. The volume percent expresses the relative ratio of molecules in the form of percent in a mixture where the partial pressure mm of Hg expresses an absolute value. Anesthetic uptake and potency are related directly to the partial pressure and only indirectly to volumes percentile. Okay. So, how do you say anesthetic agent is very potent? It should be less. You have to use it less, and it has to cause a nice effect. That is anesthesia of that patient. That's how you tell about the potency of the agent. So, as it is indirectly related to volumes percentile, it means if you use less volume, it might give more potency. So that's how you relate to the volumes percentile and the potency of that inhalational agent. Okay, the MAC value we read about in your inhalational agent class. So MAC value, this is how you calculate. MAC is minimum alveolar concentration. Okay, the agent is too potent. So it might require a dilution. It is too potent to use. For clinical purpose, we will dilute it. The splitting valve will deliver a suitable dilution that is calibrated in percentage. The valve is according to your control dial. Whatever control dial you set only, the valve will adjust accordingly. And temperature compensation mechanism work hand in hand. Every vaporizer unique design for that agent specific. That's what we need to know, because every agent will differ in their saturated vapor pressure, in their boiling point, in their vapor pressure and everything. Okay. What are the factors that affect the output of these vaporizers? Factors affecting vaporizing. First is temperature. Like I told you, increase in temperature, increase in vaporization, decrease in temperature, decrease in vaporization. Boiling point varies with ambient pressure. Okay, and ambient temperature also. Volatility, the speed of vaporization. Weaker cohesive force, less energy. It will require more vaporization. The surface area of a liquid. Surface area of liquid should be adequately high, because the fresh gas flow has to go and get in touch with this liquid. Fresh gas flow, the amount of gas you set. Gas liquid interface, again for surface area contact. Barometric pressure and back pressure. Okay, surface area of contact. Highly volatile agent will require only very less surface area. You can increase the surface area by spreading the liquid over a porous material which is folded in such a way that the carrier gas will pass through the entire surface. In our vaporizer design, we call something called wicks. Wicks will increase it is a convoluted wire-like thing that will increase the surface area contact, so that the gas has to flow in a circular manner, and while flowing through a circular manner, it will get very well contact with the liquid anesthetic agent. Mm. So you see the gas is flowing like this. You have two types, A and B. In type A, the gas is simply coming like this, flowing through the liquid anesthetic agent, getting somewhat saturated and getting out like this. Okay. In B, these are some projections inside your vaporizing chamber. So your fresh gas flow comes like this, has to go up and down and up and down. This will increase the time of vaporization, also will increase the surface area of contact. As it goes up and down, it will get more saturated. When compared to type A, type B, fresh gas flow gets more saturated with the inhalation agent. That is the idea behind the vaporizers. Okay, we have a temperature compensating valve, so that the outside temperature doesn't affect your vaporizing chamber. So according to your control dial, this temperature compensating valve will go left and right. Okay, thermostabilization. Why do we need thermostabilization? Like I told you, once vaporization happens, the temperature will fall. For vaporization to happen, we are using a lot of calories. Once these calories are taken away from the liquid only. Once vaporization happens, there is some fall in the temperature of the liquid. As vaporization continues to happen, the falling temperature continues to happen, and once at a point the temperature is so low that further vaporization cannot happen. Method to minimize temperature changes in the vaporizer is called thermostabilization so that the temperature remains stable. Vaporizers are constructed with materials of high thermal conductivity and specific heat to minimize temperature changes when in use. Methods are metal parts act as heat reservoir. Wicks are in contact with the material so that the heat loss due to vaporization is quickly replaced. Immerse the vapor chamber in a large mass of water. Temperature compensation. As you know, we are losing some temperature. We have to adequately give it from an external source so that the vaporization continues, so that the output remains stable. So, method to maintain vaporizer output constant despite the temperature changes is called temperature compensation. So how do we do that? We change the flow of vaporizing chamber and bypass chamber by alteration with the splitting ratio. Like I told you, splitting ratio will decide how much of your fresh gas will go inside your bypass chamber and how much will go inside your vaporizing chamber. For example, we have bimetallic strip in tech vaporizers. Bimetallic strip is another thing. Bimetallic rod is another thing. Okay. When temperature is high, there is more vaporization. That's what we need to know. So in this part, the temperature is high. Fresh gas flow goes. This is your bypass chamber. This is your vaporizing chamber. Fresh gas flow goes inside the vaporizer and lot of vaporization happens. And fresh gas flow gets a lot of saturated with your inhalation agent. A lot more concentration happens here, and when you get the final fresh gas flow, it is so much saturated with your inhalation agent. When the temperature is low, in the second scenario, fresh gas flow goes through your bypass chamber, goes through your vaporizing chamber, but adequate vaporization doesn't happen because the temperature is low. As you know, we need some calories for vaporization to happen. Since there is not much temperature in the inhalation agent, not much vaporization happens. It is not much saturated. As you see, by the end of the fresh gas flow, it's not that saturated with your agent. When compared to the first scenario, second scenario, it is very much less saturated. So molecules consume energy to escape and become vapor. We shouldn't let the temperature go up and down like this. We need it to be stable so that we can get a stable output from the vaporizer. Okay. So here you have a bimetallic strip that will work according to your temperature. So now temperature is high. So what will happen if temperature is high? A lot of gas will go and get a lot of saturation from the vaporizing chamber. We don't want that. We want it to be stable. When temperature is high, this bimetallic strip will close and limit the gas that is entering the vaporizing chamber. As you can see now, it is mildly closed. Only very little molecules of fresh gas flow is able to enter your vaporizing chamber. So it will expand. When temperature is high, this bimetallic rod will expand. Bimetallic because two metals will have two rates of expansion. It will control the gas that is going inside the vaporizing chamber. And only whatever we need will only get saturated and will come out. Okay, that is when temperature is high. When temperature is low, already when temperature is low, not much of vaporization will happen. So not much of saturation will, the saturated vapor you can generate. So what will happen when temperature is low? The bimetallic rod opens up and invites a lot of fresh gas flow to go inside the vaporizing chamber, because now we need a lot more gas to go inside the vaporizing chamber and to get saturated with our vapor. So that is how this bimetallic strip will help us to maintain the output normally. When temperature is high, when temperature is high, it will limit the gas that is going inside the vaporizing chamber. And when temperature is low, it will increase the gas that is going inside the vaporizing chamber. Hmm. Bimetallic strip is made of two metals with the two different coefficient of thermal expansion. These two metals are stuck together. When there is high temperature, one will expand more when compared to the other. So consider this red as another one metal, and this green as another metal, AB perhaps. So high temperature, B is expanding more and moving to one side. In low temperature, B is contracting more, moving to this side. So that is how this bimetallic strip will keep that variable ratio constant. Okay. Effect of altered barometric pressure. Most vaporizers are calibrated at sea level, that is standard atmospheric pressure. Agents with low boiling points are more susceptible to variations in the barometric pressure. Our workstation that requires that effect of changes in ambient pressure on vaporizer performance is according to their operation manuals. Okay, now we've known about barometric pressure. Now we have to know about back pressure. Again, barometric pressure, everything is calibrated to sea level. Back pressure is according to what we do. There is two sorts of effects called pumping effect and pressurizing effect. In pumping effect, the output increases. We have a desired output, more than that it happens. In pressurizing effect, it will decrease the output. So there are two sources for this back pressure. During assisted and controlled ventilation, the positive pressure generated during inspiration is transmitted from the breathing system back to the machine and the vaporizer. Assisted or controlled ventilation, okay, consider your veins ventilation. When you are ventilating the patient via veins, the positive pressure that is generated during inspiration is transmitted from your veins back into the machine and back into the vaporizer. Again, that is one scenario. Another is use of your oxygen flush. Output from your O2 flush enters the circuit downstream from the vaporizer and it activates higher pressure. So we'll see how it increases the output. Pumping effect, when resistance is applied from the to the outlet of the anesthetic machine, as during assisted or controlled ventilation, like I told you, when you are ventilating the patient via vein circuit, there is an increase in the anesthetic gas pressure that is transmitted in back to the vaporizer. We don't want anything going back to the vaporizer. This will add the vaporizer output to increase the final vaporizer output. This change is pronounced when there is already less agent in the vaporizing chamber. The carrier gas is low. There is high and frequent pressure fluctuation and a low dial setting. In a low dial setting, you will actually expect the output to be low. But what will happen when you are ventilating the patient in veins? This back pressure will go back to the vaporizing chamber. So gas that is already saturated with your vapor will again go back to your vaporizer get saturated again, and then come back. So finally, the output will be more than what you expect it to be. Okay. So this is your veins bag. Fresh gas flow comes, gets saturated with your vapor, comes out, goes like this, and goes to the patient. When you are bagging the patient via veins, this back pressure goes. The gas, this gas is already saturated with the agent that goes back to the vaporizing chamber, gets saturated. As you can see, more of the fresh gas flow gets saturated, comes back again. So this is more than your intended output. Higher concentration. When it comes out, it comes in a higher concentration. This is your pumping effect. I will explain once again. In pumping effect, you are bagging the patient. This back pressure goes back to the anesthesia machine, goes back to your vaporizer, or the gas that is already saturated with your anesthetic agent goes back inside your vaporizing chamber, gets saturated once again, and then comes out in a higher concentration. This actually happens during assisted or controlled ventilation or in a lower dial setting. In a lower dial setting, you will expect the output to be low, but because of the pumping effect, there is a higher concentration that is being delivered. Okay. How to stop this gas from going back to the vaporizer? Here you can use a one-way valve. Actually, all modern vaporizers have this one-way valve in order to prevent the gas that leaves the chamber to come back. We don't want it to come back. Okay, next is the pressurizing effect. Like I told you, in pumping effect, the output will be higher than what is desired. In pressurizing effect, the output will be lower than what is desired. Okay, in pressurizing effect, the output of some vaporizers decrease when there is back pressure. This effect is greater in higher flow, larger pressure fluctuation, and low vaporizer settings. Change in the vaporizer output caused by the pumping effect is usually greater in magnitude when associated with pressurizing effect. Pressurizing effect happens in high gas flow and pumping effect happens in low gas flow. Okay. For example, you are keeping a higher gas flow. Gas is going through bypass chamber. Gas is going through vaporizing chamber. Since there is a lot of fresh gas molecules, there is no adequate time for vaporization. It just goes fast through the vaporizing chamber and comes out. Even though you've set the dial high, you will actually get a lower concentration because you've kept the fresh gas flow too high. Okay. Next is carrier gas composition. Vaporizer output will also be affected by carrier gas composition. It changes in viscosity, density, which alters the performance of flow splitting valve. Increasing the nitrous concentration will actually reduce your agent concentration. Your nitrous is your carrier gas. Nitrous oxide dissolves in volatile agents so that effective total gas flow through the vaporizer is temporarily reduced. When the gas flow is temporarily reduced, what will happen? Vaporization will also be reduced. Your gas will not be saturated with your agent. Finally, you will get decreased concentration of agent. Why does this happen? When nitrous first enters the vaporizing chamber, some nitrous gas physically dissolves in the liquid agent, and the vaporizing chamber output will decrease until the liquid has become saturated with the nitrous. So it will take a while. When nitrous is discontinued as carrier gas, nitrous that is already dissolved in the liquid anesthetic agent comes out of the solution, in effect that additional gas flow to the vaporizing agent. The solubility of nitrous is approximately 4.5 ml per ml of liquid anesthetic. So you need to be careful while using your nitrous. So we've read about the back pressure. Back pressure, you've read about your pumping effect, your pressurizing effect, your carrier gas composition. Now next is rebreathing. What is rebreathing? Patient is breathing back whatever he or she has exhaled. So a patient inspires of O2, nitrous, your agent. What does patient expire? Patient will expire carbon dioxide, little O2 and your agent and the nitrous also. Rebreathing will cause a difference between the vaporizer setting and the inspired concentration. For this to monitor this, we need to use a agent analyzer. Agent analyzer will tell you how much of oxygen, how much of nitrous, and how much of your inhalational agent is present in the percentile of the expired and inspired gas. Okay. What are the features of an ideal vaporizer? Ideal vaporizer should be lightweight, robust and durable, easy to transport. Like, we have to transport it from a machine to machine. It should be corrosion and solvent resistant. For a long-term use, absolutely it should be corrosion free. Leak proof. We don't want the inhalational agent to leak because inhalation agents are combustible. Economical and safe to use, requires minimal servicing. We don't want frequent servicing. Usually it's annual or biannual thing. Accurate over a wide range of fresh gas flow, wide range of liquid oxygen agent levels, ambient pressure and ambient temperature. It should be unaffected by heat loss, pressure changes, downstream of vaporizer, tilting or tipping. Tilting or tipping is while you're transporting the vaporizer, if at all you tilt or tip, what will happen? The liquid agent that is in the vaporizing chamber will spill into the bypass chamber. So when you use the vaporizer for the next time, fresh gas flow will go inside the bypass chamber and the vaporizing chamber. What will happen is it will the fresh gas flow will get saturated with vapor in both the chambers since liquid agent is present in both the chambers. These are my references, Watts anesthetic equipment and Dosh and Dosh understanding anesthesia equipment for further reading. So we will do a quick recap of our session. Okay. First, we started with the difference between vapor and gas. Gas is a gas exists in gaseous state in both the room temperature and atmospheric pressure. Vapor will be in a liquid state in room temperature and atmospheric pressure. Above the critical temperature, gas will remain as gas. Below the critical temperature, the vapor can turn into liquid. Vaporizer is a device that is delivering the vapor. Vapor pressure is the amount of pressure exerted by these molecules around the container. Saturated vapor pressure is a point of pressure at constant temperature where there's 50% vapor and 50% liquid. Boiling point is the point at which the saturated vapor pressure becomes equal to their atmospheric pressure and the entire liquid becomes vapor. It is completely boiled and the entire liquid becomes vapor. And we read about the several agents and their boiling point and SVP. Okay, latent heat of vaporization is the amount of calories that is required to change 1 gram of liquid into 1 gram of vapor without any change in temperature. Specific heat is the number of calories that is required to increase the temperature of 1 gram of substance by 1 degree of Celsius. So you need to increase the boiling point by 1 degree of Celsius. How much amount of calories you need? Thermal conductivity is the conductivity of the container that is containing the liquid anesthetic agent. Okay, we learned how vaporizer works, how fresh gas flow enters, how it gets saturated, how it gets diluted. Again, factors affecting. We have read about surface area of contact, how we have this wicks to increase the surface area of contact. Then, according to the temperature, how the splitting valve works. Okay, thermostabilization, how do we minimize the temperature changes in the vaporizer? Thermocompensation, how do we compensate for the lost temperature in the vaporizer? So how the metallic rod works according to the temperature, it opens and gives away a lot of fresh gas flow into the vaporizing chamber when the temperature is low. When the temperature is more, it closes and shuts and limits the fresh gas flow going inside the vaporizing chamber. Okay. Effects of barometric pressure, effects of back pressure. Back pressure, we read about pumping effect. Pumping effect, the assisted or controlled ventilation will send the gas back into the vaporizer and get it more saturated. So the output is more than the desired output. In pressurizing effect, there is decrease in output. So that we keep a lot of fresh gas flow. There is not adequate time for vaporization, so we get a lower concentration is pressurizing effect. Always remember, pumping effect you get higher concentration, pressurizing effect you get lower concentration. How the concentration of agent varies with the carrier gas composition. What nitrous does, nitrous gets diluted into the vapor, into that liquid inhalational agent. How an ideal vaporizer should be. So these are my references: Ward's Anesthetic Equipment, 6th edition, and Oceantosh Understanding Anesthesia Equipment. You need to go through the basics of vaporizers from these textbooks so that you can understand the next class much better. In the next class, we'll be discussing about classification of vaporizers, starting from the primitive vaporizers to modern vaporizers that we use on our OTs. And we will learn more in detail about thermocompensation and Tech 5, Tech 6, and Tech 7 vaporizers and each and every working mechanism. And Draga vaporizers, Aladdin cassette, Diva and Anaconda vaporizers. All these are modern vaporizers. You can be asked all these as an essay question. So you need to know about them in detail along with the picture of their working mechanism. And about classification of vaporizers, there are multiple classification according to their vaporizing methods, according to their agent specificity. So that will also be dealt in depth. So in order to understand all the working mechanism of the modern vaporizer, you need to be strong in the physics and physical laws governing these. And You will also be learning about the safety features of vaporizers in the further class. So please again refresh your memory regarding the physics, and you can ask me if you have any questions. I guess we don't have any questions, so we'll end this session. Please do come prepared for the next class for the modern vaporizers. Thank you and have a good day.